have to worry about the oxygen because its value is 0. And our delta H for this reaction is equal to negative 1,238 kilojoules. Then we would go to our standard molar entropies for this, and we would find that for the whole reaction, 2 times the entropy of formation for carbon dioxide plus for water minus the value for C2H2, that would give us negative 97.4 joules per Kelvin. Since we're eventually going to do math with these, we have to rearrange these. Kilojoules is usually the number that ends up looking the most like a normal number. Now, what do we have here? Our standard delta G for our reaction then is equal to negative 1,238 kilojoules minus 298 K times our negative value of 0.0974 kilojoules per Kelvin. We get negative 1,209 kilojoules. So despite the fact that our entropy decreased, overall we have a product favored reaction. Why? Because this value is negative. Okay? So we had a decrease in entropy, which we would say to ourselves, well, that usually tends to make something non-spontaneous, but having such a large negative value for the enthalpy still swamps this out.
I have a question.
Sure.
Why did you write kilojoules per Kelvin on the negative 0.0974 if it's joules per Kelvin? Like, where does that go?
Where does that?
You forgot.
I forgot. So I forgot, and I realized. So this one it didn't go anywhere. I just forgot to put it in here.
Oh, okay. I was just wondering.
No, those sorts of things are confusing. So when you notice things like that, that's always a good thing to bring up. Okay? And so in this particular case, we would say that this reaction is enthalpy driven. Why do we say that it's enthalpy driven? Because a negative enthalpy, so exothermic reactions, tend to be spontaneous. We would say that a negative change in entropy tends to make things non-spontaneous. Okay? Overall, we have a negative number for this. Therefore, we say that it is the enthalpy that is driving this reaction to be spontaneous, or causing it. You can say that it's the enthalpy that's causing it to be spontaneous. Okay, so lots of times students see those words and they say, is this enthalpy driven or entropy driven? And they're not really sure what that means. Okay, so what we've decided is that we can't just look at a reaction and say, okay, I'll look at the enthalpy. That'll tell me whether it's spontaneous or not. We can't look at the entropy alone and say, okay, that'll tell me whether it's spontaneous or not. We have to look at both of them together, and if there's only one of those variables that is causing it to be a negative value and therefore spontaneous, we say that that's the variable that's driving that reaction to be spontaneous. Okay, I know that's kind of an unusual usage for the word driving, but anyway. Alrighty? So I've already, in trying to drive home the idea that exothermic reactions, it doesn't have to be an exothermic reaction. If we were to say, is the dissolution of ammonium nitrate product favored? We've already talked about this some. And if so, is it enthalpy or entropy driven? And you might even have a hypothesis as to what the answer would be, because we've already talked about this, because it's a very popular example of an endothermic reaction, and you also have solubility tables. But if we were to look up all the thermodynamic data, and if we calculated a delta H for this reaction, it would in fact be an endothermic reaction. This standard delta H is for the overall reaction. It's not for just either a reactant or a product. It's for the overall reaction. Our enthalpy is 108.7 joules per Kelvin, or 0.1087 kilojoules per Kelvin. I did it again. Golly. Sorry. All right. Okay. So, if we calculate our change in Gibbs free energy, we have 25.7 kilojoules. We multiply our entropy by the temperature, and we end up with negative 6.7 kilojoules. And so therefore, the reaction is product favored in spite of a negative enthalpy. In spite of, yeah.
It says positive.
Pardon?
It
Yes.
says positive 25, so
Yes.
that should have been negative.
This should be
25.
also, gosh, okay. Should be positive. Whoops. In spite of negative, oh, that's what I'm trying to change. And so in this particular case, we say that the reaction is entropy driven. Okay? Now, why do we say that it's entropy driven? Our enthalpy value is actually conspiring to keep it from being spontaneous, but because this is such a large increase in entropy, it is able to overtake it, and our value is still negative. And so we say that that's a reaction that is entropy driven. Yes?
So going back to the previous one where it was reactant favored, was it reactant favored?
No, they were both product favored.
Okay, so one was entropy, one was enthalpy.
Yes, it's just to show you, one has a negative enthalpy, negative entropy, but it's still enthalpy driven, right?
They both had negative and positive. That's what I'm happy.
What do you mean?
Well, I have to show it on the PowerPoint slide.
Yeah.
The answer is negative for delta G.
Okay.
Right?
Right.
And then for the next
So-
example, it was negative 6.7, right?
Right.
So then, if it's a negative negative for this one, and then positive negative for the second one, is that how we tell if it's entropy or enthalpy?
So what you're asking me about is, we did those slides with general numbers, right? Positive and negatives?
Yeah.
Okay. So if we were to, but here we have actual numbers.